Hello. Today, we're going to explore some fundamental concepts in machine learning, starting with linear regression and powerful techniques to improve it. Imagine you want to predict a house's price. A simple way is to use its size. Linear regression tries to find the best straight line that describes this relationship. The equation for this line looks like this. Here, price is what we want to predict. Theta 0 is the intercept or the base price of a house, even if it had zero size. Think of it as the value of the land. Theta 1 is the coefficient for the size feature. It tells us how much the price increases for each additional square foot. The main goal of linear regression is to find the perfect values for theta 0 and theta 1 that make our predictions as accurate as possible by minimizing the overall error. But what happens when we have not just one feature, but hundreds? Like the number of rooms, age of the house, garden size, neighborhood crime rate, or even the color of the front door. A model with too many features can become too complex. It might start to learn the noise in the data rather than the true pattern. This is called overfitting. Think of it like a student who memorizes every single answer for a practice test. They'll get 100% on that specific test, but they'll fail the real exam because they didn't learn the actual concepts. An overfit model performs perfectly on the data it was trained on, but fails miserably when it sees new, unseen data. For example, a model that thinks red doors increase house prices might work on training data, but fail completely on new houses. So how do we prevent this? The solution is a technique called regularization. Regularization discourages the model from becoming too complex by adding a penalty for large coefficient values. We change the model's objective. Instead of just minimizing the prediction error, we now ask it to minimize the error plus a new penalty term. This forces the model into a trade-off. It has to make accurate predictions while also keeping its coefficients small and the model simple. Think of it like driving. You want to get there fast, but you also don't want to get a speeding ticket. First up is ridge regression, which uses what's known as an L2 penalty. The cost function for ridge looks like this. Let's break it down. The first part, MSE, is the mean squared error, our measure of prediction accuracy. The second part is the L2 penalty. It's the sum of the square of every coefficient, multiplied by a value called lambda. Lambda is a knob we can tune. A high lambda means a strong penalty, forcing the model to be very simple. A low lambda means a weak penalty, allowing the model to be more complex. Here's an analogy. Think of the coefficients as players on a basketball team. The L2 penalty squares each player's contribution. If one player tries to do everything, their squared value becomes enormous, leading to a huge penalty. Ridge encourages teamwork, where many features contribute a little bit. The result is that ridge shrinks coefficients towards zero, but they almost never become exactly zero. It's best used when you believe most of your features are at least somewhat useful. For example, when predicting house prices, size, number of rooms, age, and location all likely contribute to the final price. Next is Lasso regression. Lasso stands for least absolute shrinkage and selection operator, and it uses an L1 penalty. The cost function is very similar to ridge, but notice the key difference. Instead of squaring the coefficients, we take their absolute value. A seemingly small change has a massive impact. Let's use an analogy. Think of lambda as a strict budget for how much importance the model can assign to its features. With the L1 penalty, the model finds that the most efficient way to use its budget is to spend it on a few very important features and completely cut funding to the useless ones. This is why Lasso is famous for performing automatic feature selection. It simplifies your model by telling you which features are not important. For example, in email spam detection, with thousands of word features, only a few words actually indicate spam. Lasso will identify these automatically. So we have Ridge, which shrinks everything, and Lasso, which selects features. What if we want a mix of both? That's where Elastic Net comes in. The Elastic Net cost function simply combines the Lasso penalty and the Ridge penalty. It has both the L1 term with its own lambda and the L2 term with its lambda. This gives it the benefits of both worlds. This is especially useful when you have groups of features that are highly correlated, like house size and square feet and number of rooms. Lasso might arbitrarily pick one and zero out the others. Elastic Net is more stable. It gives you the feature selection of Lasso and the stability of Ridge, making it a very powerful and popular choice. Its Ridge component encourages it to keep groups of correlated features together, making it more stable than pure Lasso. Before we summarize, let's discuss how to choose the right lambda values in practice. In practice, you use cross-validation to find the best lambda. You try many different values, test each one on validation data, and choose the lambda that gives the lowest validation error. Most machine learning libraries do this automatically for you. Let's quickly summarize when to use each of these models. Always start with simple linear regression as a baseline. If it works well and is interpretable, you might not need anything more complex. Use Ridge when you have many features and you believe most of them contribute to the outcome. It will prevent overfitting without removing any features. Use Lasso when you have a huge number of features and you suspect many are just noise. Lasso will help you by performing automatic feature selection. And finally, Elastic Net is often the best default choice. It's robust, handles correlated features well, and combines the strengths of both Ridge and Lasso. Remember, always start simple and add complexity only when needed. By understanding and applying these regularization techniques, you can build more powerful and reliable machine learning models. Thank you for watching and learning about regularization techniques.